What if I told you that you could print engineering grade materials on DIY consumer level 3D printers? So this is Mike, and we're at the home of Z-Polymers.
That's right,
And
Z-Polymers.
Z-Polymers, where does the Z come from?
Well, I think it's associated with my last name.
It could be. But Z-Polymers makes something called Tullomer, which you may have seen at Rapid TCT. We had this fantastic tug of war that my friend Pooch captured on video, put on Twitter, and it was insane to see. And it really sort of laid the groundwork for calling this what I want to say is a unicorn material. We get the properties of advanced materials like PEEK and ULTEM and things that people generally think of when they think of advanced industrial materials, but you printed it on a bamboo. Like, this is a consumer machine. Anybody can go pick this up. Like, a lot of people are going to get this for their birthdays or Christmas.
We're trying to democratize high-performance printing. There's about 200,000 expensive high-performance printers like these out in the market, but there's like 1 million of these. So we're trying to...
Or more.
And we're trying to be able to bring high-performance printing to people with $1,000 printers, basically.
Before we start saying this is the end-all, be-all of materials, we need to talk about some data, and we need to make sure Mike is qualified to actually make this material. So Mike, what are your qualifications for materials?
Well, to start with, academically, I have a bachelor's, master's, and PhD, and all of my research was in polymers. I then worked for a large company, Bell Laboratories, where I worked on developing crystalline polymers. I became fascinated with that material, and I ended up starting, this is my 4th company, Z-Polymers. We're focusing on 3 form factors right now. One is 3D printing, the other is making tiny fibers, and the third is making very thin woven fabrics for things like hydrogen fuel cells, essentially.
Well, okay, wait, bring this back up. This is a text, like this is almost like a fabric. So this material is this material.
Yes.
Just slightly smaller in diameter.
Yes, yes.
Well, it seems like you're qualified to do this, Mike. This is amazing. This is amazing. Like, your idea for this material came years ago, and you've iterated the process and got yourself into a part where you can now 3D print the material and make the fibers from it to make things like this.
Correct.
So if we think of materials that people use every day, first let's go consumer level. PLA, PETGs, stuff like that. Not crystalline, right?
Correct.
And very low melting temperature.
Well, some are partially crystalline, like PLA, but they all have very low levels of crystallinity, and they aren't what are called engineering plastics. They're more like commodity plastics.
Okay.
Where the properties aren't that great, basically.
For the engineering purposes.
Yes.
You know, for printing little articulated toys
Yes.
and selling it on Etsy and TikTok.
Yeah.
It's great for that.
Right.
Oh, I love it.
But PLA, still stiff. ABS, I mean, everybody stepped on a Lego. We understand the properties of ABS. Easily something that kids can play with in their engineering class or in their garage, or people print toys with. Consumer level plastics, easy. Now, above that, we start talking about things like high temperature nylon, PPS, PEEK, ULTEM. Those are going to be crystalline in nature once they're not sintered. What do we call that?
When we heat it, we basically crystallize. We make them semi-crystalline, basically.
We make them semi-crystalline.
We make them. Yeah, a material like PEEK, for example, is amorphous in the liquid state, and then when you cool it down, you can generate it's semi-crystalline, a low level of crystallinity, but then you can put it into an oven and anneal it and drive up the level of crystallinity. So it's the crystal structure that gives you good chemical resistance, gives you better mechanical properties. So PEEK is probably the #1 engineering plastic used for a variety of properties right now.
Okay. But PEEK itself, though, in order to print PEEK, you have to have a machine that can hit 450 C or more on the hot end. You need a really hot bed. You need a really hot chamber in order to print it properly. And then there's post-processing that has to happen to the part to bring it to that grade of engineering level plastics that people can then use it for, right?
Correct.
So there's a lot that has to happen, and PEEK itself is also wildly expensive. Now let's just make you forget all of that, because Tullomer is a material that you can print on the machines that PLA can print on easily, but you get mechanical properties that are going to be as good, if not better, than the PEEK material we just talked about.
The nature of our material is we've formulated it such that it can have better mechanical properties than PEEK. And it has equivalent or better properties in other areas like chemical resistance. It's V0 just like PEEK. It has a lower outgassing than PEEK. It has a lower dielectric electrical properties than PEEK. But the other interesting part of our material is that I've been following 3D printing for a while, and I've noticed that the trends in polymers is to try to improve mechanical properties in a couple different means. One is by introducing materials like ULTEM and PEEK, and also putting chopped carbon fiber and long continuous carbon fiber into materials. So what we can do is we can make a polymer that doesn't have any fillers or fibers on it, but has equivalent properties to continuous fibers incorporated into 3D printed parts. And the printers to do that are fairly complicated. But as you notice, we can make a material that has equivalent properties as a continuous fiber part in a printer like this, the bamboo printer.
And it's making it right now. What? Being able to now take the complexity out of the hardware in order to print the part, but still get the properties of the part needed, that seems like a huge advantage.
Yeah, one of the problems we're trying to solve is the fact that you just mentioned, and you know very well, that it is a complicated process to lay in things like Kevlar and carbon fiber into a plastic part. Our material, the basic concept of it is the fact that we're using materials that are crystalline in the liquid form and crystalline in the solid form like Kevlar. And so what we've done is we've taken the backbone, a similar backbone to Kevlar, and we've incorporated that backbone into our polymer. Now, Kevlar is a great material, but the issue is in order to process it into a fiber which has great properties, you have to use sulfuric acid.
You know, the thing that we all just have in a bottle in our garage, right? On the industrial side, having to use sulfuric acid, it's not that uncommon for an acid to be used in an industrial process. But again, it's still a part of the process, and you have to use it safely and dispose of it safely. There's that you have to worry about.
That's right. And so what we've done is we've been able to take, this is actually the backbone of Kevlar. And the reason why Kevlar is so strong is because of all of these aromatic rings, benzene rings. So we've taken this basic structure of the backbone and made it such that we are bonding to other long chains and making it such that we have secondary bonds that make it melt processable. So we can heat it up and melt it and then extrude it and not need sulfuric acid to extrude it, basically.
And it maintains its crystallinity throughout that entire process.
Yeah, it's basically, it's crystalline, no other polymer is crystalline in liquid form. So it's crystalline in liquid form. It solidifies very quickly into a solid. And essentially, by doing that, we can rapidly make parts. We actually print at a very high speed. That's why we like the bamboo printer, basically. And while we're extruding it, the material, we basically make the material such that in the liquid form, the molecules are lined up, and then we're basically extruding them and aligning them to a great degree during extrusion and 3D printing, and making the cross-section as strong as a Kevlar fiber, basically.
Okay.
So that's how we get the strength, is by creating this shows basically, we cut this open and the material kind of looks like wood, but it's basically fibers that we're creating in the process. So essentially the difference between putting pre-extruded carbon or Kevlar fibers into a 3D printed part, what we're doing is we're creating a fiber-like structure in situ while the material's melted and it solidifies, and we're getting similar strengths to continuous fiber parts, but basically it's all inside the process.
And the process, and you had mentioned printing fast on the bamboo, and that's one of the things that people have to realize in order to print with this, very low layer height, very fast printing speed, because you're talking about creating that fiber in what you're printing. So what's the layer height that you're typically printing at?
0.05.
I've heard some people go lower than that.
Yes, there's been one person that's gone to, I think, 0.01,
Yeah. Brendan Builds, right? Brendan Builds, I love that dude. I really want to talk about part strength. and the bamboo actually just finished. There was a Tullomer part printing while we were just talking, and it finished. And we didn't have to use sulfuric acid to make any fibers. We don't have to put it into an oven really hot in order to align the polymer chains or whatever. Like it's ready, it's done, right?
Right.
Can we take it out? Wow, that was adhered pretty well. There we go. So this part, ooh, it's nice and warm.
Yeah.
Okay, so in order to print this, 0.05 layer height, what's the temperature that this is printing
It's
at?
printed at 285. Well, the range is 260 to 300 people are printing in this printer. Yeah.
Okay, and then that bed adhesion was pretty good. So he mentioned Magigoo PC, is that right?
Yes.
Okay.
Same one used for polycarbonate. Yeah.
Yeah. And why is that? Why? So that's formulated to hold on to polycarbonate well. Is there something in the chemical makeup of this material that mimics what it's trying to hold on to in polycarbonate?
Polycarbonate has aromatic rings in it.
Oh, it does?
Yeah.
Okay.
So it sticks because it's got some of the same bonding elements, basically.
Okay. Well, this just printed, and it looks fantastic. Like it's crazy to me that we just printed an engineering grade material with properties better than these high temp materials that I've printed on 5-figure machines, and yet it just printed on a bamboo right here, and we're done. And like it's done. And all of these pieces have been like that. So let's explore the use cases that you've explored with this, because I know you've got test pieces, but like this, look at that. That's great. And so what are the advantages of printing something like this? Because normally this would be what, steel?
Yeah, like one of the advantages of our material is it's also RF transparent. So some of the projects we're working on is to replace metal hooks on autonomous boats and things like that, because we have the strength and it can't be picked up by radar, basically.
I fear you're underestimating the sneakiness.
So in thinking that way, then this material could be something that advances the consumer electronics industry.
Yes, it could be used where if there's 5G signals. So one of the interesting things is people are trying to use carbon fiber for stiffness and enclosures, right?
Yeah, oh, I've done that, yeah.
But carbon fiber actually is electrically conductive a little bit, so it can degrade.
Well, enough, right?
Enough. It can degrade signals. So this material doesn't. So it's very good from a dielectric point of view. The dielectric constant is around 3.0, and the loss is about 0.001, which is good for a polymer.
Being able to use it within those scenarios is wonderful, and being able to print at this quality is good. So this is a drone, right?
Yeah.
This seems, well, that's great because you're going to have all sorts of signals coming off of this for people that are piloting it, but you're going to get that strength you need, but it's also, this weighs nothing.
So the interesting thing too, we should point out is, aluminum has a specific gravity of 2.7 and we're 1.4, so about half the weight of aluminum.
About half.
And also you can, if you want to check this out, the state of the art for polymers in injection molding and 3D printing is to add fillers. So what people add is like carbon fiber fillers. So this is nylon with carbon fiber.
Okay.
You can check out the stiffness of that.
Do you know how much carbon fiber is in there?
I think it's about 30%.
Okay.
I believe, yeah.
And is it strand or chopped?
It's chopped.
This is chopped, okay.
Yeah.
And so it's very flexible.
Yeah, and so this is our material with no added fibers, either continuous or chopped. It's just our pure polymer, and you can just compare the stiffness of it. Yeah.
It's crazy to me because the printing process, the way you're actually producing the part is imbuing it with the properties because it's creating the fibers as it's making it.
Correct, yeah. And you can see here's a bigger test bar, and you can check out the stiffness of that. So the Young's modulus is 30 gigapascals, which is much higher. And we have a...
But it doesn't ting like a metal.
No, it tings like an organic crystal. And here basically is the properties.
Oh, I remember I saw this right here.
This,
Wait,
yeah.
I just want to make sure. This chart at Rapid is what blew my mind because I look at all these materials and then there's Tullomer at the end just beating them all.
Yeah.
Beating them all, Mike.
Right.
And that's how it's done.
And what I think is amazing is the stiffness. So these parts, for any parts that require high stiffness, I think our material is a really good solution, basically. And you can see the flex strength is, it's equivalent to Kevlar, basically, in continuous fiber parts. If you compare it to 20% carbon-filled PEEK, which is the industry leader of polymers, it's about 126 megapascals, and we're 500.
No, wait. The industry leader. So
Yeah.
it is known to industry and accepted by industry that 126 megapascals for tensile strength on carbon-filled PEEK.
Yes.
Industry standard. Everybody's like, this is great. We have these properties and we love them and we work with it.
Correct.
Now, and you're introducing something that bests it by almost 5x.
Right.
Without the complex methods for processing it. So one of the things that I thought was interesting, so Matt over there, these are compliant mechanisms.
Yes.
Right? So
Yeah.
you can do that and they do the thing. They do the thing. And he said, I printed it with Tullomer and it didn't work because it's too stiff.
That's
I mean, I eventually got it down and it did break. But in talking with Matt about this, we referenced this. And it's actually got some bend in there.
Right. It can be designed. It can be designed now. That's the design feature. Yeah.
Right. Well, that's what I'm really curious about because you have a material where the mechanical properties can change depending on the height at which you extrude it and the speed and the temperature at which you extrude it, right?
Right.
So then you can make all-in-one parts with the same material where different pieces of the part have different mechanical properties.
Correct. With polymers, the end part properties are a function of the material formulation and the processing. They go together.
They go hand in hand, right?
They go hand in hand. So what we've done is we've formulated the material with the right monomers in it so that we can extrude it into 1.75 millimeter filament, which was not easy, but we've developed a process to do it. We've also developed the right viscosity.
Well, when we talk about viscosity of material, I don't think it's really something that people consider too much.
Yeah, viscosity is basically, it's when you give something shear stress or shear rate, basically it's the thickness of the material. It's like, is it laminar, is it turbulent? How easy is it to flow? Does it flow like water? Does it flow like ketchup? Does it flow like mustard? So it's basically the thickness of it as it comes out of the nozzle, basically.
Oh, I see,
and,
I see.
And these types of materials by themselves, if you try to print them, they won't print. So what we've done, that's part of our sort of IP, is developing the term is called rheology, but viscosity versus temperature and shear rate to make it extrude into a filament and to be able to extrude it in a machine like this.
Okay.
And as I said, one of the key things we did was we also formulated with the right monomers. So you could extrude it in a machine from like say 260 to 300 degrees centigrade, whereas with ULTEM and PEEK, as you well know, you've got to be 400, 450 and all that.
In talking about this material, like I firmly believe a material like this can change the world because of its properties, especially knowing that the machines behind us aren't the ones that can only print it. Like you can print it on these machines.
Can I bring up another point too?
Absolutely.
You mentioned changing the world. I started the company thinking about the things that you just mentioned. I wanted to develop this new material that didn't require long carbon fibers and could be better than PEEK and ULTEM and things like that. But also, people these days care about climate change and the environment.
Sure.
And so one of the things that we've learned after making this material and studying it more is that if you make 1 ton of carbon fiber and you make 1 ton of Tullomer, we give off 100 times less greenhouse gases in the manufacturing process. So it's just another.
That's cool.
It's another feature of the material. Yeah, and then the fiber area.
Here, let's hold this. Look at this. This is not thread. This is not something I'm gonna make a T-shirt out of.
No, this is 50 micron fiber that we're making in manufacturing, and that gets we basically take that and that gets woven into a very thin structure. And this is going into basically fuel cells because it's very strong and allows the fuel cell membrane to be much thinner, and that would basically make hydrogen to be more a viable source for energy, basically. So the value of it is the fiber is very strong, so you can make it very thin and you can weave it very thin because it's so strong. So, but also, as I mentioned, that fiber, people are using glass fiber and carbon fiber. In the manufacture of glass fiber is the same as carbon fiber because of all of the high temperature operations. It gives off a lot of greenhouse gases. The other environmental issue also that we've been approached on, you've heard of Teflon, PTFE,
Yeah,
right? So
very familiar.
So, there's several materials. The key to that material basically is fluorine carbon bonds.
Is that why if it gets too hot, it could be dangerous to breathe the fumes?
Yeah, exactly. And people have heard of the PFAS problem, which is in the manufacture of that material.
The forever chemicals.
The forever chemicals, exactly. So we're getting approached by several companies to have our material replace that type of material because it's much more environmentally friendly.
Let me ask you real quick, because you were talking about Teflon, and people used to have Teflon lined pans when they would cook stuff.
Yes.
Can you have Tullomer lined pans?
Genius.
This was the thing that we played with at Rapid. You want to give it a go? Stop it. And this was just like this was printed on that machine.
Right.
Yeah.
So this one's 1 gram, I believe. Yeah.
1 gram. And it took 3 of us on either side to pull it apart. And that was after lots and lots of people tried pulling it apart.
Right.
So Mike, this has been an amazing discussion. Like the level of things that we talked about were so deeply nerdy that people are really going to enjoy this. And in preparing for our shoot here, we had talked about how we could get people interested. We want people to submit project ideas for Tullomer, right?
Right. The material's new, and as I say, printing it, it's not like printing PLA or nylon. It's different. We've developed some pretty good profiles for it, but we want to have some fellow travelers that want to help us find the best applications for the material and basically wanted to help develop process profiles for it. So what we're going to propose is make a proposal on our website for a project, and then if we like the project, we think it's reasonable, we'll give you some free material to work on it.
Yeah, so there'll be a link down below in the description. And the idea being, if you have an idea for Tullomer, it's amazing and you can print it on consumer level 3D printers. So if you have an idea for a project that can take advantage of some of those properties, go down below, click the link, and send it to Mike and the Z-Polymer crew, because they're going to be watching that. And they want to find people, like you said, fellow travelers who want to go along this journey of developing the Tullomer material and the processing for it. And I might send you an email. I might have some ideas. We'll see.
Yeah.
This was a wonderful chat with Mike. Actually, you know what, Mike? The floor is yours. Tell everybody where they can go to find out more about Z-Polymers and Tullomer.
The website is www.z-polymers.com. That's our website. Joel believes that this is a breakthrough in polymers for 3D printing, and we want people to be our partners. We'd love to work with you to provide some free material for you to develop a project with it.
If you have an idea, you might get free material. That's amazing. Well, thanks for watching with us today, and thanks for making this far. If you did, you're awesome. Don't forget to hug each other more, fight for a cause you believe in, and print all the strong things. And as always, high five. Nailed it.